This is Physics 2212, Lab 3, magnetic field of a bar magnet. The purpose of this lab is to better understand how the magnetic field due to a small bar magnet is affected by a distance from the magnet using a magnetometer, and it also helps us to visualize magnetic fields and magnetic dipoles. Some fundamentals of the Biot-Savart law and the bar magnet distance dependence formula. Were the magnetometer and bar magnet. Procedures: in order to determine where the magnetometer chip was on the phone was slid perpendicular to the ruler to find the position at which the magnetic field was the strongest. Find the on-axis magnetic field distances. A ruler was used to measure the on-axis distances from the phone to the bar magnet. However, when graphed, these values are linear, so the natural log was taken to linearize them. To find the off-axis magnetic field of a bar magnet, the phone was placed at a distance in the x direction at which the magnetic field was 100 microteslas. Next, the phone was slit in the y direction by the same distance. At a very large distance from the bar magnet, the magnetometer measured a value very close to 0 for the magnetic field in the x direction. As the distance in the x direction from the bar magnet to the magnetometer decreased, the magnetic field in the x direction as measured by the magnetometer increased. The magnetic field due to Earth will interfere with the measurements of the bar magnet's magnetic field if the magnetometer on the phone is in position correctly. Some calculations. The distance dependence formula that I got was negative 3.01x minus 14.598. N is the slope, which is negative 3.01. I had to find the k value from the natural log of k, which was 4.57 times 10 to the negative 7th. Then I set the Biot-Savart law equal to dependence equation to solve for mu, and I got mu equals 2.285 amperes times meters squared. Here's my glow script code. It's physical constants, creating the magnet origin, the magnetic moment, visualizing the magnetic field on axis and perpendicular with different observation locations and arrows to represent the magnetic fields. And these are the perpendicular axis arrows, and this is the off-axis magnetic field visualization. This is the output model with each of the magnetic field vectors, the distance, and the off-axis magnetic field. The theoretical off-axis field was 2.7 times 10 to the negative 5th teslas, whereas the experimental off-axis field was 6.3 times 10 to the negative 5th teslas, which is about 80.6% difference, and the magnetic field at the 45-degree angle off axis, the distance d, was 8.5 e to the negative 6, 2.5 e to the negative 5th, 0. It's pretty likely to be accurate because the magnetic field of a bar magnet, as shown on the right, is very similar to that of a magnetic dipole. Some error sources could be the location of the magnetometer on the phone. Because if placed incorrectly, the magnetic field of the Earth could interfere with the measured values we get for the magnetic field due to the bar magnet, and also the calibration of the magnetometer is pretty important. If it's not calibrated correctly, then it could lead to false results or incorrect results. What if you hadn't oriented your experiment to compensate for magnetic north and had instead laid out your meter stick at some intermediate angle with respect to the Earth's magnetic field? How would your results have changed? The Earth's magnetic field would actually interfere with the measured values for the magnetic field, skewing the results. And if you were to stick two identical magnets together end to end and run this experiment again, how would the measurements differ? The measured values for magnetic fields would roughly double, and their directions would remain the same. Conclusions: the distance dependence and Biot-Savart law equations can be used with bar magnets to yield accurate results. The distance has a significant effect on strength of magnetic fields, and bar magnets can be used to model magnetic dipoles.